So a vector in R2 is just a matrix that has one column or one row, and it has two components. So just as an example, vector u, let's call it 3, -2. It has two components. You can call it an x and a y component. We would just generically say if it's u, we would say the first component is u1, second component is u2. And you could graph this, let's say 3 in the x direction, -2 in the y direction. We would draw an arrow with its endpoint at the x and y component, first and second component of the vector. So this would be vector u. And to add two vectors, let's say I've got 3, -2, and let's say v is 1 and 4. If I'm going to add u and v, all I have to do is add their corresponding components. So I'm going to add the first components together. I'm going to add the second components together. And it's very simple to get the sum. In scalar multiplication, that means you're going to multiply a constant times a vector. So for example, what's 3 times u? Well, that just means you're going to multiply 3 times every component of the vector. So this is pretty easy as well to remember. You just multiply that scalar times each component of the vector, and you get a new vector. Okay. So in this example, we have u and v, and we're asked to find 4u -3 times v, and then 4u plus -3 times v. So let's do 4u first. So 4u, that's a funny looking u. 4u is 4 times 1 -2. So we're just going to multiply that 4 times every component. So we get 4 and -8. -3v is going to be -3 times 2 -5. And again, we're going to multiply inside. That's going to be -6 and +15. And then last, 4u plus -3v. I'm just going to write -3v. So that's just this 4u that we already found plus this -3v that we already found. And then in this addition problem, we just add the components together. So it's going to be -2 and 7. So that is 4u minus 3v. So we only have addition and scalar multiplication, but if you multiply by a negative number as your scalar, then you get subtraction as well. Right? So this is the same as 4u plus -3 times v. Right? And if you're in R2, we have this parallelogram rule for vector addition. So just as a generic example, let me use this arrow function. This might be better. If I've got this vector and I'm going to add this vector, call this u, call this v. The parallelogram rule says that if I take this vector maybe a copy here, and I place it onto the end of the other vector. So I just made a copy of u and placed it on the end of v, and then draw my new vector from the origin to that endpoint. That's supposed to be a vector. Then the resulting vector is the sum. So when you add two vectors, you form this parallelogram, and if I make a copy of this guy, that didn't work. If I make a copy of the other one and place it on the end, if I make a copy of v and place it on the end of u, we get the same thing, and it forms this parallelogram shape. It's a rectangle that's been knocked over, right? It's got a slant to it. The angles aren't 90 degrees. It also turns out that if you subtract the vectors, you get this opposite diagonal. So this diagonal would be u minus v, and this diagonal is u plus v. So let's just try that out. I've got a graph here. We've got two vectors. We're going to add them, and then we're going to graph the result. In fact, let me make this bigger so we can see it better. So let's add u and v. So I'm just going to add the components here. So 1 plus 3 is 4, and negative 2 plus 2 is 0. So I get 4, 0. So I'm going to draw my vectors here. 1, negative 2. And you'll check me if I mess up here. That's 1, negative 2, right? 1 in the x direction, negative 2 in the y. And then let's do again for 3, positive 2. It's going to be this vector, right? So let's just label these real quick. This is u, this is v. And I'm going to make a copy. Let's make a copy of u. Do this, clone. And I'm going to place that at the end of v. And you see where the endpoint is here. If I now draw my resulting vector, the sum, it's right down the x-axis, and that is u plus v at 4, 0. So that's exactly what we got. So that's called the parallelogram rule. So you can actually add vectors just by graphing them. If you're in R2, you could probably do it in R3 if you've got a good imagination. So now what happens when you scale a vector? If you multiply by a scalar, what does that mean? So let's just perform these operations real quick. What's 2 times u? That's going to be 2 and negative 4, right? We're just going to multiply the entries by 2. And then what's 0.5u? So 0.5 times 1 is 0.5, and 0.5 times negative 2 would be negative 1. So let's draw these. So u, again, is 1, negative 2. Let's see if I could change the color. Let's do this in green. 2u will be 2, negative 4. You can see when I go down to 2, negative 4, that green vector is right on the line with the black one. And let's do it again for 1/2. I'll do this in red. So 0.5 and negative 1 is right here. So we've got u is the black, 2u is the green, and 0.5u is the red one. What if I did negative 2 times u? What's that? So that would be negative 2 and positive 4. So let's see what that looks like. And I'll pick a different one. Let's do blue. So negative 2 and 4 is right here, and you can see that one is also on this line. So multiplying by a scalar literally just scales that vector, and it points it in the same direction unless you multiply it by a negative number. The negative is going to flip it over, but it's still going to line up on the same line. And 2u is a vector that's going in the same direction as u. It's just going to be twice as long. 0.5u is the same direction as u, but half as long, right? So that's why we call these constants in front of the vectors scalars, because they are literally scaling that vector, making them longer or shorter. Okay, and you can flip the direction, but it's going to be on the same line. So vectors in Rn just means you can have vectors of any size. So if it's an Rn, then you've got n entries in the vector. It's however many that is. Okay, so you could have 100 members, you could have 1,000 members, you could have 3 billion members in the column, right, or in the vector. So n, the superscript of this notation means how big the vectors are. How many entries does it have? The R just tells you that the entries are real numbers. So Rn is just a vector of size n with all real numbers as the entries. And the 0 vector is just a vector that contains all zeros. Okay, so we can write 0 with a vector sign. Sometimes we just write the number 0, and it's kind of understood that it's a vector if you're dealing with vectors. And there are properties of these Rn vectors that are very similar to properties of just real numbers. So you can add them together in any order. That's called the commutative property. You can group the additions. That's called associative property. If you add the 0 vector, you get the same vector. That's called the additive identity, right? This should be familiar from your algebra class. If you add the negative, you get 0, which that's called the additive inverse. When you multiply a scalar times the sum of 2 vectors, you can distribute that scalar. It's like it's this distributive property. It also works if you're adding 2 scalars and multiplying that times a vector. You can kind of distribute that vector to each scalar. And if you've got 2 scalars, it doesn't matter what order you multiply those in. You can multiply one scalar times a vector and then the other, or you can multiply the scalars together and then multiply times a vector. And if you multiply vector times the scalar 1, you get the same vector. That's called the multiplicative identity, right? It doesn't change.